Okay, so in today's talk we will conclude the topic of Shannon's theory. Okay, so in the previous class, if you remember that we had concluded with the idea of equivocation of keys. Okay, so we have defined briefly that what is the idea behind spurious keys, right? So today we will try to understand whether we can compute a lower bound of the spurious keys. Okay, so if I just would like to recap that we essentially proved this particular formula yesterday, that is hk given c is equal to hk plus hp minus hc. Okay, so therefore the ambiguity of a key given the ciphertext is described as follows, that it is addition of the ambiguity of the key plus the ambiguity of the plaintext subtracted with the ambiguity of the ciphertext. Okay, so we also discussed about what is the meaning of ideal ciphers and told that in case of an ideal cipher, hk given c is equal to the value of hk. So that means that a ciphertext does not leak any additional information about the key, right? So these are the things that we described yesterday and concluded with it, and so therefore hk given c gives us the idea of the security or insecurity. Okay, so therefore what we discussed is that even for perfect ciphers the key size is infinite if the message size is infinite. So that was the problem with perfect ciphers, that is they were not practical. Okay, so then we defined another kind of ciphers called the ideal ciphers, where hk given c is equal to hk. Okay, and as I described yesterday, that the main objective of our what we study in this course would be to find ciphers which are secured against a bounded adversary. That means we are essentially striving to achieve computational security. That means security considering what is today's computational power. Okay, so for example, if we can prove that a given cipher has got a security which requires an adversary to do say 2 power of 80 computations, then we are fairly happy. We say that the cipher has achieved computational security. Okay, so the question is how to protect. So therefore, but still, I mean, in today's class we will be essentially still considering an unbounded adversary and essentially address this question, that is how do I protect a data against a brute force attacker with an infinite computational power. Okay, so therefore there is an attacker who has got infinite computational power, and still can I protect a cipher. So the idea is that there is Shannon defined a certain parameter which is called the unicity distance, and he said that that is the least amount of ciphertext which I would like to make it available to the adversary, who is an unbounded adversary, so that he does not find out the unique value of the key. Okay, so the strategy of the adversary is as follows. What he does is that he takes the ciphertext, he assumes a key, decrypts it back, and finds out a plain text. If the plain text is meaningful, then he notes it down. Okay, but the point is that because of the redundancy in the English language, or rather any other any language for that matter, the adversary will not actually find out the key uniquely. So what he will essentially have, he will have a set of keys. Okay, so apart from the actual key, the other keys are called the spurious keys. Okay,
now how will the attacker say that the message is meaningful? Like if he is doing some iterations, and how will he actually decide? How will the computer decide that the text is meaningful? You cannot check each and every text.
No. So the idea is as follows, that is you take the ciphertext, consider a shift cipher. Okay, so you have got a unique value of the key, right? So you find out a value of the key. So what you do is that you decrypt it back, and then you check that whether the plain text makes sense or not. So what you are asking is that you have got a lot of work to do, but what I told you at the beginning is that I am considering what? I am considering an unbounded adversary. So the adversary has got infinite computational power. He is supreme. Okay, so the idea is that the question is that whether even given such a kind of adversary, how many minimum number of ciphertext will I make it available to the adversary so that he cannot still guess the actual value of the key. Okay, so therefore the set of the spurious keys should be null.
There is a minimum number or maximum number?
Minimum number, because if I give you more information, then you can do more things, right? So I would like to give the adversary minimum number of ciphertexts, right? Is it clear? Okay, so therefore a common misconception is that any cipher can be attacked by exhaustively trying all possible keys. Okay, this is a very common misconception. So what we would like to say is that, for example, even if DES, okay, it has got a 56-bit key, so this can also be broken by brute force, right? But the idea is that, so suppose let us consider an adversary who can do 2 power 56 computations, so he should be able to break it, right? So the idea is that, but if the cipher is used within its unicity distance, then even an all power adversary cannot break the cipher. Okay, so because of the strategy is therefore what you take the cipher text, you decrypt it back, check the plain text whether it makes sense or not. If it makes sense, you note the key, okay, and keep the key, register the key as a meaningful key, okay, or rather a possible key. But there is only one key which is the actual key, the rest are spurious keys, right?
The significance of unity distance, sir?
Yes.
Significance of unity distance.
The significance of unicity distance is that, for example, if I can compute the unicity distance of say DES or any other cipher, then I would like to use the same key for so many times. After that I have to change the key if I am considering an unbounded adversary, right? So for example, if I am considering an unbounded adversary, then I would like to use the key only for say 2 times. After that I would like to change the key if its unicity distance is 2. Okay. So therefore this is what I have just described. So Hk given C is the amount of uncertainty that remains of the key after the cipher text is revealed. So we know it is called the key equivocation. We have already defined that. So what the attacker does is that he guesses the key from the cipher text, and it shall guess the key and decrypt the cipher. Okay. So what he does next is that he checks whether the plain text obtained is meaningful English or not. If not, he rules out the key. But due to the redundancy of language, more than one key will actually pass this test. Those keys, apart from the correct key, are called spurious. So then we come to something which is called, we have already discussed about what is entropy. So we will be using this, we will be using entropy to find out a minimum bound of the spurious keys. Okay, so we will try to find out a minimum bound or lower bound of the number of spurious keys. Okay, so therefore consider HL. So therefore HL is used to measure the amount of information per letter of meaningful strings of plain text. Okay, so that is the definition of HL. It measures the amount of information per letter of meaningful strings of plain text. Okay, so therefore consider a random string of alphabets. So there are 26 letters, and if all of them are equally likely, then what is the entropy? It is equal to log 26 base 2, right? And so that works to computes to 4.76. Okay, but English language, have a probability distribution. It's not 1 by 26 for all the letters, right? So this is a sort of a graph which shows how the English language characters in general vary. So therefore, if you just do a first order entropy, that means you just take one particular alphabet among and consider its probability, and then you feed into the formula of pxi, log pxi, negative and sigma. Okay, then your first order entropy of the English text works to 4.19. Okay, but you can do better than that. So you know that in English language, consecutive letters essentially are not uncorrelated. For example, if I take Q, the next letter is U. Okay, so they are not uncorrelated. So that means that if I take 2 grams, for example, this entropy or uncertainty should reduce, right? So therefore, if in the first order entropy is not enough, so what you do is that I do a second order approximation. So in second order, what I do is that I compute all possible diagrams, I find out their probabilities and subsequently their entropy, and then I divide that HP square, okay, by 2. So it works to 3.9. So you see that the entropy has reduced, right? Similarly, you can do trigrams and again find out the HP 3, and then again divide that by 3, and similarly you can do higher order approximations of the entropy. Okay, so the idea is that in general the successive letters have got correlation which reduces the entropy. Okay, so therefore, for example, define that an higher order entropy as follows, that define HL as the entropy of a natural language L, as HL is equal to limit n tends to infinity HPN divided by n. Okay, so you find out the value of HPN, means you find out all n grams, their probability distribution, compute the corresponding entropy, and then divide this by n. Okay, and your limit n tends to infinity. That means this is an approximation for very high values of n. Okay, and it has been found experimentally that the value of HL, if you consider very high values of n, in general ranges between 1 and 1.5. Okay. So you will find that HL falls within 1 and 1.5. So from there, what do we understand? We understand that there is some amount of redundancy in the language. Okay. So in order to understand that better, let us quantize the redundancy by using this parameter, say RL. RL is defined as 1 minus HL divided by log cardinality of the plain text base 2. So you can immediately understand certain terms from this formula. For example, we will find that RL is equal to 1 minus HL. So therefore, if you just consider a random language, that is, if English language would have been random, then what would have been the entropy of HL? It would have been log p base 2, right? So in that case, what would have been the redundancy? It would have been 0, right? So therefore, you see that for any other value of HL, like when I am considering say 2 gram, 3 gram, 4 gram, 5 gram and say n grams, then this value of HL was gradually reducing. So that means the redundancy was increasing. So therefore, this formula is able to capture the redundancy of the language. Okay. So for example, if for typical values, if you say that okay, HL lies between 1 and 1.5, so you take a value of so for example, let us consider this, that is 1 minus HL divided by log of p base 2. Okay. So in that case, I can rearrange this as follows, because I will be using this later on. So I can write, for example, HL divided by log p base 2 is equal to 1 minus RL, right. So therefore, HL is equal to 1 minus RL into log of cardinality of p base 2. So we will just note this equivalent relation, because we will be requiring this result subsequently. Okay. So you note one fact, that if this value of HL, that is if HL reduces, then the corresponding, this implies that the corresponding value of RL increases. Okay. So therefore, if the entropy reduces of the corresponding language, that is equivalent to saying that the redundancy of the language has increased. Okay. So therefore, this formula is able to capture this intuitive result. Okay. So let's let's consider what is the corresponding redundancy of an English language. Okay. So we would like to quantize that. So if you find out, you will find out that HL lies between 1 and 1.5. So consider that HL is equal to 1.25, and you know that the number of plain text characters are 26, right. So therefore, if you feed into this formula, your RL works to 0.75. So what does it mean? It means that English language is 75% redundant. Okay. So whatever you speak, out of that 75% is actually redundant. So does it mean that out of 4 characters you talk, I can throw away 3 characters? No, it's not exactly so. Okay. So what it only means is that if you do, for example, a Huffman coding, then essentially you are expected to get such a kind of compression. Okay. So therefore, that is the idea of redundancy of a language. Okay. And that is precisely the reason why cryptanalysis is favored. If you had a very random kind of language, then cryptanalysis would have been harder. Okay. But you know that there is a redundancy in the English language, and that serves as an extra information to the attacker. Okay. So let us try to calculate the lower bound of equivocation of the key. Okay. So that is the objective of today's class, the first part of today's class. So for example, I have already defined you n grams. So consider Pn and Rn and Pn and Cn to be 2 random variables defined to represent n grams of the plain text and n grams of the cipher text. Okay. So all of us know already this formula. So it is what this says: Hk given Cn is equal to Hk plus Hpn minus Hcn. So this formula we have already proved in the last day's class. Yes. So what is Hpn equal to? So Hpn we have defined from the definition of HL. If the value of n is quite large, you can approximate that by nhl. Okay. And you know that HL by my previous result was equal to 1 minus RL log cardinality of p base 2, right. So therefore, if I would like to calculate the value of NHL, I would have just need to multiply this particular thing by by n. So, I get n into 1 minus RL into log of cardinality of p base 2. So, that is the value of NHL, right. So, therefore, I can say from here that HPN, which is approximately equal to NHL, I can write that as equal to n into 1 minus RL into log of cardinality of p base 2, right. And the next thing that I want is h of Cn. Okay. So, I write that h of Cn is equal to, or rather is less than equal to, n of log of cardinality of C base 2. Why? Now, because whatever be the entropy, so I am considering n grams. So, this is equivalent to saying that h of Cn by n is less than equal to log of cardinality of C base 2, right. So, all of us know this fact, right, because this essentially captures the entropy of a random ciphertext, right. So, whatever be it, the entropy that is divided by n should obviously be less than a random thing, because this has got the the maximum entropy, most uncertainty, right. So, therefore, this value is obviously lesser than this. So, we will be using these two bounds in our calculation. Okay. So, one bound is given by h of Cn is less than equal to n log cardinality of C base 2, and the other approximation is h of Pn is approximately equal to n into 1 minus RL log cardinality of P base 2. Okay. So, we will plug these equations, these two things into our equivocation formula that we had. So, the formula that we had was h of k given Cn is equal to h of k plus h of Pn minus h of Cn. So, we have a fair amount of estimate of Hpn and Hcn. So, if we plug that, we get this value, that is h of k given Cn is greater than equal to h of k minus n RL log cardinality of P base 2, right. So, do you see that? So, you see that if I subtract Hpn minus Hcn, then these particular terms, that is n log cardinality of P base 2 minus n log cardinality of C base 2 gets cancelled if the cardinality of P and C are same. Okay. So, if I just consider that both of them are English letters, for example, then the cardinality of P and cardinality of C are the same thing, right. So, they are the same value. So, therefore, they cancel each other, and we have got a lower bound of hk given Cn, which says that hk given Cn is definitely greater than hk minus n RL log of cardinality of P base 2. Okay. So, therefore, let us remember this formula, so that because we will be needing this later on. It says that h of k, if I write it in the other way, minus n of RL log of cardinality of P base 2 is lesser than equal to h of k given Cn. Okay. So, now we will try to prove an upper bound of hk given Cn, that is hk given Cn should be lesser than equal to some term. So, from there we will try to find out quantize the value of the spurious keys. Okay. So, till this part is clear.
So, is this independent of the size of the key?
Yeah, we have not assumed anything of the key. So, for example, we have just assumed that the ciphertext cardinality and the plaintext cardinalities are the same, but the key is, we have not assumed the size of the key. This calculation is independent of that information. Okay. So, therefore, consider possible keys. So, therefore, ky, just define ky to be the possible keys given that y is the ciphertext. Okay. So, define this set. So, what does it mean? It is that possible keys given that y is a ciphertext. So, I have already defined what it means. It means that ky is a set of those keys for which y is a ciphertext for meaningful plaintexts. Okay. So, therefore, as I told you that a cryptanalyst takes, or an attacker takes the ciphertexts, assumes a value of key and finds out those keys or registers those keys for which the plaintext is meaningful, right, and that is denoted by the set ky. So, therefore, the ky set holds those keys for which the corresponding plaintext is meaningful, right. So, out of these keys, how many are spurious keys? Cardinality of ky minus 1, right, because only one key is the actual key, rest is spurious, right. So, therefore, we know that when y is a ciphertext, number of keys is modulo of ky. So, out of them only one is correct, right. So, rest of them are spurious. So, the number of spurious keys can be found out by cardinality of ky minus 1. So, what is the expected size of cardinality? So, you know that this is actually a distribution, right. So, therefore, in order to calculate the expected value of a random variable, what do? We multiply the corresponding value with its probability and do a sigma, right. So, I guess we know this result, that if there is a random variable x, then its expected value Ex is computed by sigma of its corresponding probability into xi, where I runs over all possibilities, right. So, that is the way how we calculate the expectation of a random variable, right. So, we apply this and we find out the expected number of spurious keys. So, what is the expected number of spurious keys here? It is the average number of spurious keys over all possible cipher text, and this is denoted by the variable Sn. Okay. So, Sn is nothing but sigma of cardinality of ky. I mean, we are just multiplying cardinality of ky minus 1, because this is the number of spurious keys, and we are multiplying that by the probability of this event. So, what is the probability of this event? That the cipher text y is chosen, right. So, that is py, and that is varied for this calculation is done for all possible cipher texts. Okay. So, you know, if I just simplify this formula, then I can actually multiply this sigma, this py with ky, and I obtain that this, if I distribute this py over 1, then I obtain sigma of py. So, what is sigma of py over all possible cipher text? It is unity 1, right. So, I get sigma of py multiplied with the cardinality of ky, and that from there I subtract the value of 1. Okay. So, this gives me what? This gives me the expected number of spurious keys, right. So, therefore, from here I can write that Sn plus 1, I can just reorganize this equation. I can write Sn plus 1 is equal to this particular thing, right. So, therefore, I can write like Sn plus 1 is equal to sigma of py cardinality of ky, where I varies over all possible cipher texts, right. So, this is actually also we have this also we can put down from the definition of Sn. Okay. So, therefore, if you need to calculate the upper bound of the equivocation of key, we do for further calculation from the definition of Hk given Cn. So, what is Hk given Cn? So, but as I told you that there are two random variables here, k and Cn. What we do is that we let's vary one random variable and keep the other one constant, right. So, therefore, we vary in this case y, and we keep the value of k constant. Okay. So, therefore, from our definition of conditional entropy, we can write that this is equal to sigma of py multiplied by h of k given y. Okay. So, this we have actually written in last day's class, you can follow that. So, therefore, this is equal to, actually this inequality should be actually an equal to. Okay. So, this is equal to sigma of py, I just write this as ky. So, therefore, what does it mean? It means k given y, right. So, that is exactly the definition of h, that is exactly the definition of ky, right. So, I obtain the sigma, I multiply py with hky, and I take the corresponding sigma. So, now this is less than equal to py multiply with logarithm of cardinality of ky base 2 and taken as sigma. Now, this follows from what I already told you, that if this ky would have been a, so I mean, if for example this h of I mean this ky would have been a random distribution, right. In that case, this would have been upper bounded, I mean this would have been equal to logarithm of cardinality of ky base 2. For any other distribution, this uncertainty is lesser than a random distribution, right. So, therefore, I can actually find out an upper bound, and this is the upper bound. Okay. Then I apply a certain result from mathematics, it is called Jensen's inequality, but it is applicable for the logarithmic series because it is a monotonically increasing function. Okay. But let us just believe this fact that I can actually find out an upper bound of this, which is called, so I can upper bound this particular thing by this expression. Okay. So, I can take the log out and I can take this, write this as follows. Okay. So, what is this particular sigma equal to? This sigma is equal to Sn plus 1 from this result. You see this, that is sigma of py cardinality of ky was equal to Sn plus 1. Okay. So, we use this result and plug into that equation. you will obtain this. So, you see that this is equal to sigma of py cardinality of ky, and instead of this I can write Sn plus 1. So, what we have proved is that hk given Cn is less than equal to logarithm of Sn plus 1 base 2, right. So, what we have proved is hk given Cn, okay, is less than equal to logarithm of Sn plus 1 base 2, right. So, now we can actually take this result and we can combine this fact and obtain that, and rather write that hk minus n of RL logarithm of p base logarithm of cardinality of p base 2 is less than equal to logarithm of Sn plus 1 base 2, right. Is it okay? So, that is precisely written what here. So, I write that hk minus n RL log cardinality of p base 2 is less than equal to logarithm of Sn plus 1 base 2, right. So, therefore, I can actually reorganize this and rearrange this and write as logarithm of Sn plus 1 base 2 is upper bounded by hk minus n RL log cardinality of p base 2. So, now if the keys are chosen equiprobably, that is if all the keys are equally likely, then I can actually write that this as an equality, right. I can write that hk is equal to logarithm of k base 2, right. So, in that case I can plug this into this previous equation and this works out to this equation. So, this is this inequality. So, I can obtain that Sn plus 1, Sn plus 1 is greater than equal to cardinality of k divided by cardinality of p to the power of n RL. So, this follows from this equation. If you plug in the value of hk and make it equal to logarithm of cardinality of k base 2. So, just see that if I take this and if I plug here, then I can actually write this as logarithm of cardinality of p base 2 to the power of n RL, right. And from there I obtain a log here, and this is also a log. So, the subtraction of log would be log a by b, right. So, therefore, I can write that as logarithm of cardinality of k divided by cardinality of p to the power of n RL base 2, right. And on the left hand side I have got Sn plus 1. So, therefore, since I have got two logs on both sides and we have got an increasing function, I can actually write that Sn plus 1 is greater than equal to cardinality of p cardinality of k divided by the cardinality of p to the power of n RL. Okay. So, what do we obtain from here? What is the objective? The objective is what is the value of n? What was n? N was the number of ciphertext that I had provided. Okay. So, therefore, now I would have liked to make the number of spurious keys equal to 0. That is the object. That was the objective finally, right. So, unicity distance says that thus increasing n. So, we obtain from here that if I increase the value of n, then that reduces the number of spurious keys. That means what? If I provide an attacker more and more information, then the number of spurious keys get reduced, right. So, unicity distance is that particular number of ciphertext. So, I call it n0, for which the number of ciphertext or rather the number of spurious keys is actually reduced to 0. Okay. So, if I, for example, in the previous equation if I had made the value of n, so I can actually write that, okay, if I just plug in 0 to that previous value, I would have obtained this bound. You see this, that is, if this was equal to 0, then I would have obtained we would have obtained what? We would have obtained that cardinality of k divided by cardinality of p to the power of n RL is equal to 1, right. So, that means that cardinality of k is equal to cardinality of p to the power of n RL, right. So, therefore, that is exactly this particular equation. You see that n is equal to logarithm of k base 2 divided by RL log p base 2. Okay. So, actually in my equation I can take log on both sides and I can write log k base 2 is equal to n RL log cardinality of p base 2, right. So, what is the value of n here? It is equal to log of cardinality of k base 2 divided by RL logarithm of p base 2. Okay. So, this is the value of n for which my number of spurious keys just becomes equal to 0. Okay. So, for unicity distance would be greater than that. So, therefore, if I had provided you more and more ciphertexts, then actually your number of keys would have been 0, right. So therefore, if I use a cipher within this unicity distance, then the number of spurious keys will not be 0. So that means the attacker is not able to exactly find out the unique value of the key. Okay, and we have so throughout our calculation we have actually considered an unbounded adversary, right. So even an unbounded adversary would not actually find out the actual value of the key, not the unique value of the key, but he will have a set of possible keys, right. And unicity distance is actually that number of ciphertexts for which this number of spurious keys just becomes equal to 0, right. So therefore, we obtain this particular lower bound. So therefore, this is a lower bound of the number of spurious keys, number of for the lower bound for the unicity distance. Okay, so I mean beyond that is actually the attacker is able to find out the unique value of the key. So note that this calculation may not be accurate for small values of n. Why? Because my original HL definition relied upon the fact that limit n tends to infinity. So that was an assumption that I made, right. So therefore, this may not be very much true for n equal to 1, 2 or so on. Okay, it should be fairly okay for large values of n. Okay. So let's do an example calculation of with the substitution cipher. So we had number of plain text characters equal to 26. So the cardinality of p was 26. Cardinality of k was 26 factorial. Okay, so that was around 4 into 10 to the power of 26. So a fairly large value of the key. So your RL, if you assume, is equal to 0.75 of English language, then if you plug in, you will find that n0 is approximately equal to 25. Okay, so that means that given a ciphertext string of length 25, an unbounded attacker can actually predict the unique value of the key. Okay, so thus what we observe from here is that a key size alone, such a large key size, does not guarantee security if brute force is possible to an attacker with infinite computational power, right. So an attacker who has got an has got an infinite computational power, right, for him such a big size of key, actually he requires just 25 ciphertexts to actually find out the value of the key. Okay, all these measures are of course probabilistic, but it will match with the actual result quite closely, right. So with this we essentially conclude this part of unicity distance, but we will conclude the remaining part with an idea of product ciphers. So actually after this we will actually start talking about real ciphers like block ciphers and stream ciphers. But before this, I would like to mention about the idea of product ciphers. So this was actually also mentioned in Shannon's paper, and that's why it's called a seminal paper. Okay, it was mentioned as old in 1949, and he gave the idea of forming products. Okay, so the idea is still fundamental because even present day ciphers like AES, for example, still uses the concepts of product ciphers. Okay, so let us try to understand the concept of product ciphers, and actually you will observe that through that lot of things becomes meaningful. Okay, lot of things which we will see in our future ciphers will actually become meaningful. Okay, so let's try to see. So before that, I would just like, in order to simplify our life, I will just coin a term called endomorphic ciphers. Okay, so what is an endomorphic cipher? Endomorphic ciphers are those ciphers for the plain text and the ciphertext are the same sets. So for a normal substitution cipher, your plain text and ciphertext were just English language, English characters, right? So if P and C are the same, then we have what is called an endomorphic cipher. Okay, therefore the shift cipher of on English language on English alphabets was an example of an endomorphic cipher. Okay, so consider an endomorphic cipher, and let's try to understand certain things from history. Okay, so therefore if we have an endomorphic cipher, say C1, you note that I have written P comma P because P and C are the same things, right? The plain text set and the ciphertext sets are the same things. Okay, so I write P comma P and then follow that with K1 because K1 denotes the key set of the encryption function C1. Okay, so that is the cipher C1, and you have got an encryption function E1 and a corresponding decryption function D1. You also have a cipher which is called C2, and I denote that with P comma P comma K2 comma E2 comma D2. So that means what? The K2 is the set key of the keys for the second cipher, E2 is the corresponding encryption function, and D2 is the corresponding decryption function. Okay, so let us try to understand or define what is meant by the product cipher C1 cross C2. So what does C1 cross C2 means? It just means, like, as you know, that you apply two functions one after the other. Okay, so therefore if I say C1 cross C2, it means that first I will apply C1 and follow that with the application of C2. Okay. So, I think you have seen this in the case of composition of functions, right, in discrete structures class, right. So, therefore, this is exactly precisely similar kind of thing. So, you see C1 cross C2 I would define as P cross P because it is still endomorphic. You see why it is endomorphic? Yeah, because I mean repeated application also still keeps its endomorphic property, right. So, it is still endomorphic, but your key set is the Cartesian product of K1 and K2, because that is K1 cross K2. Okay. And you have got the corresponding encryption function E and decryption function D. Okay. So, any key I can write in the form of an ordered pair K1 cross K1 comma K2. I can form ordered sets like that, right. So, the encryption function is defined as E equal to E2, and but initially you take the plain text X, you take the key K1 and you apply the function E1. Okay. Subsequently, you choose a key K2 and you apply the encryption function E2. So, what will the corresponding decryption function look like? The corresponding decryption function will look like this. It will look like D equal to D2 D1 Y comma K1, follow that with K2 like this, right. So, do you see that if I apply D and E subsequently, they are actually inverses of each other? That is obvious because of the associativity of the product rule. Okay. So, actually you can see that, because if I apply D, okay, and if I apply D over an application of the E function, then actually I obtain back where I started with. Okay. So, you can see this because of this yeah, it will be first D1 and follow that with D2. Yeah. So, that you can obtain from the decryption function, because what you do is that you take the corresponding so you write this E2 E1 X comma K1 comma K2. So, that is my Y, right. So, I take this as a Y and I apply my D over that. So, therefore, what I do is that I want to compute this, right, I want to compute dy. So, for that I apply D1 D2 over E2 E1 X comma K1 comma K2, okay, and then so this is my okay. So, therefore, this is my E1. Okay. So, therefore, what I do is that I have actually encrypted so this is my scope of the function E2, then I apply D2. So, in order to decrypt this I need K2 and follow that with K1, right. So, what you do is that you see that in this case your D2 and E2 cancels each other. So, I can do that because of the associativity of the product function. So, if I do that, I obtain D1 and I obtain then E1 X of K1, okay, comma K1, right. So, again this D1 and E1 cancels each other and I finally obtain back the value of X. So, therefore, you see that D is actually a corresponding decryption function, right. So, this follows because of this fact, that is the product rule is always associative. Okay. So, the question is that if we can compute product of ciphers, does the cipher become stronger? That is what is most important, right. So, I take two small ciphers and I compose them, I compute the product. Does the cipher become stronger? That means, does the key space becomes really larger? So, in the initial, I mean on the surface you have actually K1 comma K2, right. So, the Cartesian product size should increase, but on a second thought, does it really become larger? So, in order to understand that, what is your opinion on that? Will it really become larger? Will the key size will become larger? So, actually not always. Okay. So, let us try to consider one example. I guess it will be a lot clear through that. So, let us consider a simple multiplicative cipher. So, what it does is that it just takes X and multiplies with A, where A is co-prime to 26. So, you know what is co-prime? So, A is co-prime means its GCD of A and 26 is 1. Okay. And next is you consider a shift cipher where you take X and you add that with K. Okay. So, therefore, this is my M and this is my S. Okay. So, this was an example of what? It was an example of a permutation cipher, okay, and this was an example of a substitution cipher. Okay. So, now you consider that, for example, that you have got M and you have got an S, right, and what you do is that you just compose this M cross S and you obtain this, that is y is equal to ax plus k. Is okay? You see, you first of all have, so you need to first do the multiplication. So you do ax, and then you need to do s. So you add k with ax. So what is the key in this case? The key is the tuple a comma k, and you know that this is an example of what? It is an example of affine cipher. So what was the key size in case of English language? What was the size of affine cipher? It was equal to 312. Okay. So now you consider s cross m. So s cross m is equal, y is equal to ax plus k. So that is, you can also write that as ax plus ak, right? So now you know that GCD of a comma 26 is 1. So therefore this is also an affine cipher, and the key would be a comma ak. But since the GCD of a and 26 is 1, so a inverse exists. Okay, this we discussed, and actually there is a 1-to-1 relation between ak and k. Okay, so therefore the total size of the key space in s cross m is still 312. So you see that here we have got the key ak, and here we have the key k, right? But since there is an inverse of a, there is actually a 1-to-1 correspondence between this set and this set. So if there are 26 possibilities of k, then also ak, since you are doing a modulo 26, also has got 26 possibilities. So that means this set and this set are essentially the same things, right? So that means in both the cases, you do m cross s or you do s cross m, your key size is still 312. Okay. So what you see is that m cross s and s cross m are same. So that is what is called commutativity, right? So we have got a commutative ciphers. Okay. So it means that m cross s and s cross m, when they are same, we call them to be commutative. Okay, and this is an example of a commutative cipher. It doesn't matter whether you do first shift and then multiply, or you do first multiply and then shift. Both are the same things. Okay. So then let us see what is an idempotent cipher. So therefore, what is an idempotent function? It means if we apply the same function twice, you obtain back the same function, right? So therefore, in m is a permutation cipher, s was a case of a substitution ciphers, and both of them were actually idempotent ciphers. Okay. So a composed cipher has a larger key, but no extra security, because m cross m, if it is equal to m, then even composing m's for, more than that, more than once, essentially leaves you with the same kind of transformation, right? So essentially it does not add to your security. So therefore, for example, if we had computed m cross m or s cross s, that wouldn't have led to the increase of the key space. Okay. So this is because s cross s and is equal to s, and m cross m is also equal to m, and these class of ciphers are called idempotent ciphers. Okay. So you could easily observe from this fact, that is, if I had done m cross m, what would have been what would have that meant? I would have done ax and then aax, right? But my key size wouldn't have still increased, right? Because doing a square essentially doesn't increase the key space. Similarly, consider for shift cipher, you do one shift and you do another shift. So in both the cases, you can represent that that by a third shift, right? So do you understand what I'm saying? So what I'm saying is that if you consider, say, s as x plus k1, for example, okay. So I'm just considering s cross s, okay, and I'm just trying to argue that s cross s is actually equal to s. So what is the idea? So if you imagine that in the first phase you have got the function as, you choose the key as k1, okay, and in the second case you choose the key as k2. So on the first application of s, I would have computed x plus k1, and in the second application of s, I would have computed as k2, right? So therefore I would have obtained x plus k1 plus k2. So that, since I am doing a mod 26, I can always represent that as x plus some k3 mod 26, where k3 is nothing but the summation of k1 and k2. So that means even for s cross s, I have got the same size of the key, right? So it's the same cipher. So therefore I can conclude that s cross s is equal to s, right? Similarly, for m cross m also, you can actually show that m cross m is also equal to m. So both these classes of ciphers are something which we call as idempotent ciphers. Okay. So therefore we have defined what is a commutative cipher, and we have defined what is an idempotent cipher, and what we will now consider is that what happens if we compute the product of such kind of ciphers which are commutative as well as idempotent. Okay. So actually that we can observe from this fact. So therefore what we are trying to observe is that there is no point of obtaining products of idempotent ciphers. So if you take m cross m, it's the same thing as m, right? So there is no point of doing such products. So rather we would get product ciphers from non-idempotent ciphers, that is by iterating them. So if we had some non-idempotent ciphers, I would have liked to iterate them, and that is essentially the concept of round which exists into all classes of symmetric ciphers in today's world. Okay. So the question is how to make non-idempotent ciphers or functions. Okay. So if the idea would be that compose two small different crypto systems which do not commute. Okay. So do you follow this? If you don't follow, then this will become clear because of this calculation. So what I have said here is that if there are two crypto systems which are idempotent and also commute, then their product is also idempotent. Okay. So if this result is true, what does it mean? It means that if you have got two crypto systems which are idempotent and also commute, then their product is also idempotent. So what does it mean? It means that if you obtain a function of this class, okay, then if you take and if you take them and if you still product or rather compute the products of those kind of ciphers, the key size doesn't increase, right? So therefore considering products doesn't help. Okay. So therefore from this theorem or rather this result, we know that we actually require to compute the products of ciphers which even if they are idempotent, they do not commute. Okay. So that explains this point, that is compose two small different crypto systems which do not commute. So those kind of ciphers, if we iterate them, will actually make sense. Okay. So therefore let's see this result. It's quite simple. It says that S1 and S2 are two such crypto systems which are idempotent and at the same time they commute. So S1 cross S2 cross S1 cross S2. Okay, so I am considering the product of these things. So therefore, so if I observe that, okay, from the associativity I can write like S1 cross S2 cross S1 cross S2, and since this commutes, S2 cross S1 becomes equal to S1 cross S2, right? So now you know that S1 cross S1 is equal to S1 and S2 cross S2 is also equal to S2. So what you have obtained is that S1 cross S2 and product and multiplying that with S1 cross S2 essentially leaves you with S1 cross S2. So what does it mean? It means that this is an idempotent function. So in your previous case we had proved that m cross s, m and s were essentially both of them were idempotent, right? So therefore can you understand why m cross is also idempotent? Why? No, because we had proved that m cross m was equal to s cross m. So it means m and s were commutative, and we had also proved that m cross m is equal to m and s cross s is equal to s. So that is they were idempotent as well. So if you compute their products, then essentially you are left with the same thing. So therefore computing their products or composing them doesn't help, right? So therefore you require some other additional quantity which will help you. Okay, and that is the idea of rounds. So therefore the idea is that how can you what is that feature? So till now whatever we have seen, there is a feature missing which we have not yet seen. Then therefore the concept of round we are still not able to achieve. Okay, so what is that concept? That concept is of nonlinearity. Okay, but I will define that nonlinearity concept further in our subsequent classes, but this is a brief introduction to that. So therefore consider that instead of let's consider these two functions s and p, where p is actually equal to x plus k, okay, and s is the output of a function fx. Okay, now I claim that this function is actually a nonlinear function with respect to addition operation. So what does it mean? So it means that therefore what does a nonlinear function mean? It means that if you consider f of x1 plus x2, so nonlinear with respect to plus, nonlinear is always with respect to an operation, right? So f of x1 plus x2 is not equal to f of x1 plus f of x2, and equality would have meant linearity. Okay, so therefore now consider this function s equal to fx and p equal to x plus k, and consider s cross p. So what is s cross p equal to? It is equal to fx plus k. And what is s cross p cross s cross p? So that means that you take fx plus k and then you do a further application of f and add that with k, right? So for this multiplication to increase the value of the length of the key, so thus what is needed? So therefore it is needed that s cross p should not be idempotent. Okay. So if that, so what we require is that f of fx plus k, which is equal to this particular thing, when it is added with k, should not be equal to f square x plus k dash, because if this, I mean if you had a linear function f, then you can actually if this was a linear function, you would have actually distributed this, and this would have computed to some f square x plus some value of k dash. Okay. So that you see is exactly similar with your s cross p function. It's some other application of f, and it's added with the key k, right. So therefore therefore this happens only if f is nonlinear with respect to plus. Okay. So if this was a linear function f, then actually this would have distributed, and the result that we would have obtained would have been similar to that of s cross p, right. So the size of this function, the size of the key of this function and the size of this composed function would have been the same. Okay. So therefore what we need is something, a deviation from this fact. So we need not linearity, but we need non-linearity. Okay. So therefore hence we have to compose linear and non-linear functions to increase the security of a cipher. Okay. So in order to increase the security of a cipher, what we have seen till now are only linear components, linear transformations. Okay. We essentially found out multiplication with a matrix, which is a linear operator, addition with a key, that is also a linear function, right. So therefore all these are linear transformations. Okay. So therefore you see that nicely from Shannon's theory we can actually arrive at the fact that we require a composition of linear functions and as well as non-linear functions. Okay. So with this I conclude my talk, but I would like to give you an assignment which you are supposed to again do it and submit it on 20th, before 20th. Okay. Both I have given you one assignment already. The other assignment is that show that unicity distance of the Hill cipher with an m cross m encryption function is actually less than m divided by RL, where RL is the redundancy as defined in the class. Okay. So you can show that the unicity distance of the Hill cipher with an m cross m encryption function is actually less than m divided by RL. Okay. So that is an assignment which is given to you, and you can read further things from Shannon's book, which is Communication Theory of Secrecy Systems. It is actually a paper. It's a classical paper, so it's Bell Systems. It appeared in Bell Systems Technical Journal, but I'm sure you will get online. And the other textbook that I have followed is from Douglas Stinson, Cryptography Theory and Practice. A second edition book is you can follow, so I followed that book. Although a third edition exists. And next day's topic would be symmetric key ciphers. So we'll use these concepts to go and build ciphers now. Okay, so therefore symmetric ciphers is our next day's topic, and we will start with block ciphers and follow that up with stream ciphers.